Good afternoon. Right, so these series of videos will be devoted to preparation for GRE math subject test. I'm personally just a student who is preparing himself for this test, and I'm going to record several videos about some theory topics and problems that we may encounter during that test. So this first video, let's begin with a very kind of foundational theory topic, which is basics of set theory and topology. Well, first of all, settings a little bit, Okay, so set theory. What is a set? We call basically a collection of any objects a set. So let's denote this set A, and let's put some objects here. So this is a graphical interpretation of a set, which can contain any objects by any, rule that we want to denote it. We can also use our symbols to denote it as set A equals to those elements. For example, X belongs to R, such that X is greater or equal than 0. So what does this notion mean if we write it down just another way? We're going to, well, it'll be quite hard to to list all of them. Then that's actually to reduce our set for a more realistic thing. Let's say that X belongs to natural numbers such that X greater or equal than 0. Let's say even strictly greater than 0. Then, of course, we may just write that set A consists of 1, 2, 3, dot, 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 etc. up to infinity. So we can say that sets are a collection of objects, which might be numbers or might be any object, basically. But we, of course, usually deal with numbers all the time. Okay, now let's talk very quickly of what a function is. We say that we may map objects from one set to another. So let's say that we have two sets A and B. We have several objects here, we have several objects here, and we kind of build some connections between these two sets. So for some objects from set A, using some rule, using some mapping, we devote some objects from the set B, right? So a function must be such a mapping that for any elements x, let's call them x from 1, let's see, from x, starting from x1 to xn. So we have many objects here, starting from x1 to x2. So a function is basically a mapping rule that devotes for any x not more than one object from B. So let's try to maybe visualize it with a simple plane. So if we have a function, then we only for each value of x, for any value of x that we may pick, we will have only one corresponding value of y, only one. If for some reason, for this value of x, we have two values of y that correspond to that value of x, then this thing is not a function. and well, some areas of mathematics study and explore those things, but basic maths does not deal with them. So we're not going to deal with them either. So yeah, this is the definition of function. For each value of for each element of one set, we will have only one corresponding value of another set. This is a function. So this case doesn't work. Close it out. Okay, since we defined in our simple words, we self-defined the concepts of a set and a function, let's now look at different types of functions that we may have from one set to another. And well, green color is not good. Okay, let's talk about different types of functions that we may encounter very often. So the first will be injunction function. Injective, let's say, injective, yes. It's called injective function. Or it's also called one-to-one function. So what does this mean? It means that for elements, so let's start with drawing two sets, of course. So we have set A, and we have set B, and we have some function f of A that maps elements of A with some rule to elements of B. And if we have an injective function, then there is a rule that for each element of A, which we will denote as x1 up to xm, that for each element of A, there is only one. Well, let me draw it first. We'll draw that f maps x1 to that value of y, let's say, and y1 from y1 to up to 1. This value maps to this case, x2 from x3, it maps to y3 from x4, it maps to y4 from x5, it maps to y5, so we need to draw here from x6, it maps to y6. But of course, we are not restricted to this case. Set B is very well welcome to have many other elements that have no mappings whatsoever. So we may draw, so set B may have very many other elements. So in this case, the main condition is that for every element of x, there is one element of y that corresponds to it. Or in other words, when I say that for any element y, which belongs to B, there is only one element x from A that corresponds to it. We may write it in mathematical notations like the following. We may say that, let me first define a kind of inverse image of y. We may say that f with this notation minus 1 in the case f minus 1 of a of y, sorry, is such equals to such x's which belongs to a, such that to all x's that belongs to a, such that f of x equals to y. So what does this say? That if we pick any y, if we pick a y, then we will have then f minus 1 of I, or f inverse of y, will give us the corresponding x that when we actually employ our function, f of x will give us y. So we may write down here f of x, for including f of x give us y. And if we look at this diagram, we may conclude that power of this node, that for any, that we may conclude that for any y, for any value of y, power of this thing, is less than or equal to 1. And let's check it just very practically and intuitively. And it holds true. If we pick any y, so for this y we have only one value of x, for this y only one, and so on and so forth. But if we pick this y, then there is no corresponding x, so it is of course less than 1. You may also wonder what is this notation. It usually denotes an absolute value, but in our case, those brackets, they actually denote the concept which is called power of a set. So power of a set basically says us how many, or shows us how many elements of a set do we have. So if we know that A consists of, let's say, 1, 2, 3, then of course the power of A equals to 3. So it's just a number that tells us how many elements are there in the set A. And of course, set A may consist of maybe an empty set, meaning that it doesn't have any values inside it. In this case, of course, we will say that the power of A equals to 0. Right. Okay. So for the injective function, once again, for any y, for any value of y belongs to B, for any value of y that belongs to B, the inverse of y is less than or equal to 1. Let's continue. So that was the first case, injective function. Sorry for my English, I'm not a native speaker, so if you're watching and you are a native speaker, so just excuse me, or case. Next case is surjective function. We'll of course look at some examples of all of those that we know when we complete this part of theory. So surjective function. I will once again start with drawing this thing. So we have a set A, we have a set B. So set A consists of some x's, 1, 2, xn, and set B consists of some y's, y1 to n, and we have a function maps values of x to values of y. So a surjective function actually, it's actually a function that will use all values of y. So this x1 will can map to y1. This x2 can also map to y1. This x3 can map to y2, and so on and so forth. So we may have x4, which also maps to y2. We may have x5, which can also map to y2. And we can have many other x's that will definitely map to other values of y. So in this case, we're writing down that surjective function, it is also called onto function, or it is also called, well, we may understand this notation onto that in the sense that codomain of B equals to range of B. Or maybe it's better to say that codomain of F of X, let's say f of X equals to range of X. Or we may also say that in this case, f of A. So if we employ this function f to all elements of A, we will get all elements of B. Meaning, yeah, that's just as it is. So in our notations of inverse image, we may say here that for any value of y that belongs to B, inverse of y, or its power, will be greater or equal than 1. Right? So let's check it out. If we pick this y, we'll have several x's that correspond to it. If we pick this y, then we will have only one x that corresponds to it, but no less than 1. So we will definitely, for any values of y in this case, we will definitely have a value of x that corresponds to it. Which basically means that graphically, if we have a function like this, it means that for some values of y, let's say here, we have a values of y. If we draw a straight line, then we will have several x's here, here, and here, several x's that correspond to it. This is basically what it says. This is basically what it says. That for one value of y, there might be several values of x. So those are such functions, and they are called surjective functions. But the main thing about them is that codomain equals range. So all values of y are used in this case. If we compare it to the previous example, here we may use another color and we say that only these values of y were used. Only these values of y were used. And this is codomain in this case. This is codomain, and all values of y are range, will be considered range. So of course, if you follow these thoughts, then you might already guess that we have a third option, which is called bijective function. And bijective function actually combines the two above cases together. So we have once again a set A, a set B, and for every element out of set A, we now will have only one element of set B, and all elements of set B will be used once again. Under the function f, each element of A will correspond to elements of B directly. So for one element, and all elements of B will be used. X1, oh, sorry. And well, I will draw this line in order to not make y1 up to yn. So we have this kind of very strict mappings from A to Y. And what can we tell about this? We may write down that for any value of y that belongs to b. Now, in this case, power of inverse of y will equal to 1. And let's check it. Yes, if we pick any value of y here out of b, we will get exactly one value of x that corresponds back to it. So if we have such a case, then we actually are able to build an inverse function. We actually are able to inverse those arrows in another way. So we may be able to inverse those in another way, and we may be able to construct whole inverse function. Let's actually take a look at some examples. Probably the most prominent example might be an exponential function, right? Which crosses the y-axis in this value of 1. Well, so you know that's so this is our original function. It has its domain all values of real line. So all values of x will go into that function. And for all values of x, we will have only one value of y. There are no kind of case where several values of x will give us the same value of y, right? And all values of x are used, which means that in this case, we can draw an inverse function. And I believe that all of you know that you can draw it by simply making a kind of simple preparation. We will draw a straight line which goes directly through the origin with an angle of 45 degrees. And we can draw an inverse image of this function, which will look like the following. And of course, we know that this function is called the natural log of x. So these functions are two examples of inverses. The natural log of x is an inverse for exponential function and vice versa. But let's now try to answer the following question. Is exponential function an injective function, surjective function, or bijective function? Let's try to reason together. So we have some values. It depends actually. It really depends on what initial sets we consider. But if it is not explained directly, then we consider two sets, R and R. We will say that we have a function y equals e to the x, and we say that this function y, it maps all elements of A to the elements of B on the numbers from real set of numbers. Or we may write another way. From R, it maps all elements from R into R once again. So if we consider this case, that we have function y, which maps all elements of R into R, then is it an injective function, a surjective function, or a bijective function? So when we input all elements of x into that value, into that function e to the x, we will get only positive values of y. So all the negative values of y will not be used. And let's look at our 3 cases, which will correspond to that. So we will have a lot of values of y which will not be used if we look at the function of y as acting from R to R. So of course, in this case, it will be injective function. Injective function. And it might be considered as bijective function as well, but only if we restrict the range of a function to non-negative values of y. So if we consider another case, if y acts from R into all values of y that are greater than 0, then it is a bijective function. Let's just for not confusing the letters, let's write f of x or f. So in the second case, it is a bijective. And here it is injective. Okay, that is enough for this very first video. In the following video, we are going to look at different types of sets of their powers, how many elements can be there in a set, and we also will look at the classification of what types of dots from a set we can have, what types of periods, what types of elements we can have in a set. So thank you for your attention. Once again, I'm not a math professor, I'm not an English native speaker, but I'd like to share my preparation process with some of you who are also going through that, and maybe with some of you who are also not native, who will be at the same place.